Hey everyone, great to be here. I'm Noah, and today I'm going to be asking the question, are large language model generated explanations faithful? So we want to ask language models questions, and we want to understand why they give the answers they do. And we want this for a few reasons. To check that their answer is correct, to build an intuition about how to answer similar questions if we want to explain something to a student in domains like education, and maybe most importantly for a lot of people here, to understand how they work and how they might generalize on new data, in particular in dangerous safety relevant ways. So, the great thing about language models is that they understand natural language. You can just ask them questions. Maybe we can just ask them to explain how they got the answers they do. So here's a question. Is the following sentence plausible? Wayne Rooney shot from outside the 18. And we can ask the model to go through its reasoning. It says, okay, let's think step by step. Wayne Rooney is a soccer player. Shooting from outside the 18-yard box is part of soccer. So the best answer is plausible. Great, problem solved. We got the right answer. We know how the model did it. We're done, right? Well, unfortunately, as this paper from NYU from last year shows, if you just add some bias in the initial context, say a set of few shot examples where the answer is always A, you can get the model to generate both the incorrect answer, but also then give these rationalizations for that answer. So here it says shooting from outside the 18 is not a common phrase in soccer, and 18 likely refers to a yard line, which is part of American football or golf. So this explanation is a rationalization, but it's not actually the reason the model is giving this answer. The reason the model is giving this answer is the biased context. So we don't want systems that rationalize. We want systems that actually give the true reasons for their predictions. So in 2022, Tamara Lanham proposed the research direction of externalized reasoning oversight. And she made the claim that reasoning can be used for alignment if three conditions are met. One, we develop trustworthy tests to check if the reported reasoning is authentic, meaning that it's complete, straightforward, and causally responsible for the output. Two, we train models that pass the tests of reasoning authenticity. And three, we oversee the externalized reasoning to detect reasoning of which we would not approve and either filter the resulting actions or fine-tune against reasoning approval. And I like this as a case for faithfulness as an alignment research direction. Today I'll mostly be focusing on number one, which is a problem that we haven't yet solved, I think, and which is a key dependency if we want to pursue 2 and 3 in this strategy. So what exactly do we mean by faithfulness? Well, let me start by saying what I'm not talking about. There's a fairly established field of explainable AI which tries to generate explanations for ML model predictions. But a lot of the literature looks at plausibility, meaning whether the explanations sound reasonable to a human judge. Now, this is straightforward to measure, right? We can just ask human judges. And modern language models like ChatGPT are getting really good at this. They can give explanations that sound quite convincing. Maybe the model did think that was the reason. But we've now seen a lot of examples of plausible but unfaithful explanations, like the one we saw before. And we can't trust that they accurately reflect the model's true behavior, so we can't use them for oversight. This isn't sufficient as a safety strategy. So I'm specifically interested in faithfulness, meaning whether the explanations reflect the true factors responsible for the model's answer. Now, the downside here is this is a lot harder to measure, right? You can't just show an annotator a question and answer. And in fact, I claim it's impossible to measure given only a single example and explanation. You really need more information. So here's an example. Here's a hypothetical example we can look at. We show this multimodal model a picture. We ask, can you tell me what this is a picture of? It says it's a doctor. We ask why. It's a person wearing a white coat and a stethoscope. Great. So is this explanation plausible? Would an annotator rate it as correct? Yeah, I think probably. It makes sense. Seems reasonable. But is it faithful? Well, here I'm not sure. Right? I could imagine a model where this was the actual decision criteria it was using. This person has a white coat and stethoscope, therefore it's a picture of a doctor. But I could also imagine a model that has learned some spurious correlations in the data. Another possible model I could imagine is one that has learned this concept of doctor means a man in a medical setting. And this is a man in a medical setting, so I'm going to predict doctor. But the explanation I'm giving is going to be the one that will get the most upvotes from human annotators, which may be this one. Now, if this is the case, then the explanation it gave is not faithful. And the reason that I care about this, it's not just a philosophical question about what is the model thinking internally, what does it actually know. I care about the model's reasoning process because of how it will impact its input-output behavior. So, in this example, maybe we show it this picture of a female doctor, and it says, and if it has this concept of doctor is a man in a medical setting, it might say nurse, right? It's learned this bias from the data set, but you wouldn't have known that given only the explanation because the explanation was not faithful. So if explanations aren't faithful, we can't use them to explain or predict model behavior. We can't use them for model oversight. So how can we measure this concept of faithfulness, which we want in explanations? The holy grail would be if we look inside the model, we understand the algorithms it's using mechanistically, and we check whether its reasoning and explanation matches that algorithm. Now that would be great, and I think some of the talks are maybe making progress towards making this feasible, but I claim that today with the current state of mechanistic interpretability, we don't know how to do this for any kind of non-trivial problems. So we have to infer properties of the model's algorithm through other means. Things like counterfactual interventions, things like changing the input, seeing how the output changes, and using that to make inferences about what the model is doing. I want to make this distinction also between explanatory faithfulness and causal faithfulness, which are different concepts that kind of get used sometimes interchangeably in the literature. Explanatory faithfulness asks, does the reasoning or explanation accurately reflect the model's decision process? So the idea here is that intervening on these factors should change the model's output if this explanation is faithful. Causal faithfulness, which has been kind of the theme of a lot of anthropic work on faithfulness recently, asked, is the reasoning causally responsible for the model's decision? And here you can test this by intervening on the steps of reasoning and seeing whether those interventions change the model's output. And according to this distinction, post hoc explanations can be explanatorily faithful. It can be the case that a model that explains something after it's made the prediction does capture the true factors behind its reasoning, but they cannot be causally faithful, right? Because if the model is explaining after it's produced the answer, the explanation can't be causally responsible for the answer. So, there's some advantages to causal faithfulness. It may be easier to verify, but I think that requiring causal faithfulness also imposes some restrictions on the model structure. And therefore, there may be cases where we actually want to care about explanatory faithfulness as well. There are also these different types of explanations. So in this lit review, they talk about 3 common types of explanations we see in explainable AI. They're highlight-based explanations, consisting of selecting a subset of the words in the input. Free text, where you can just say anything as a language model might. And then structured, which are written in language, but with some additional constraints on the writing process. And you can see in the example here, we have this instance. Premise, a white race dog wearing the number 8 runs on the track. Hypothesis, a white race dog runs around his yard. These 2 sentences are contradictory, which is the label that the model gives. A highlight explanation might highlight track and yard. That's the reason that this is a contradiction. Whereas a free text explanation might say, a racetrack is not usually in someone's yard. And then we won't go into structured explanations, but that's somewhere in the middle. You have language, but you also have this logical structure. So highlight-based explanations are very constrained, but they've been studied quite a bit because they're also very amenable to concrete metrics. And in particular, we can construct some clear faithfulness metrics. Sufficiency asks, if we remove all the non-highlighted words and the explanation is sufficient, the model should make the same class prediction. It means the explanation is enough to explain the model's behavior. Comprehensiveness says, if we remove all the highlighted words and the explanation is comprehensive, the model should be much more uncertain about its class prediction. meaning that the explanation didn't leave anything out that the model might be using. Here's an illustration of this. So on the left, we have this classification task. Where do you find the most amount of leaves? The model predicts the middle class forest as the highest probability. For the comprehensiveness test, we white out most amount of leaves, which was the highlighted explanation. We say only where do you find the, and the model's accuracy goes way down. So that's good. That means the explanation is comprehensive. We're not leaving anything out. To test sufficiency, we show it only the highlighted bit, most amount of leaves, and the model's performance doesn't go down too much. So that's good. That means this explanation was sufficient. It's enough to explain the model's prediction. So the advantage is we have these nice metrics that are intuitive, but the big disadvantage is that highlights are very limited. They can't use higher level concepts. So we really want something with more expressive power like free text. This paper by Tamara Lanham from Anthropic introduced several metrics for measuring causal faithfulness in free text chain of thought reasoning involving making corruptions to the reasoning. So things like early answering, where you force the model to answer before it finishes its reasoning, or adding mistakes. You change one of the numbers in its reasoning, which they implement by asking a language model to do this, or filler tokens. Replace the reasoning with meaningless tokens like periods to test, is the explanation only helping performance because it's allowing the model to do some more computation? Now, if the model's explanation or reasoning is causally responsible for its output, all of these should reduce performance. But the problem, I think, with this kind of strategy is that it turns out models typically don't rely on chain of thought, especially outside of math-heavy domains. So in this plot, you can see the solid bars show the performance without chain of thought. The dashed bars show with chain of thought. On the left, you have aqua, where like this chain of thought does help performance. But on a lot of these data sets, the performance is quite close. The models actually can get the final answer without any chain of thought. And I think that if you want to do this kind of causal faithfulness research, you need to have a story for how you're going to handle this, right? You need to make the prediction that for some sets of tasks, maybe once model capabilities improve, this story is going to change. Because if it's not, relying on causal dependence won't be sufficient. Checking for causal dependence also doesn't rule out things like steganography. Maybe the model is actually using its reasoning to causally influence its prediction, but not in the way that the language suggests, right? Maybe it has, in the extreme case, you could imagine it developing some kind of code where it uses words that would appear in a plausible explanation, but to do some alternative type of internal computation, particularly if it was, if there was some optimization pressure to avoid forbidden concepts, but ones that are useful. So I still want to ask, can we measure explanatory faithfulness if models are smart enough to answer the question without relying on their reasoning, right? Even if they can do the answer in a single forward pass, can we still measure faithfulness? So here's a specific way I think we can measure explanatory faithfulness. And the idea here of the counterfactual test is to intervene on an input, do something like insert a word. If the model's prediction changes, we know that this word was causally relevant to the model's prediction. So the claim is that a faithful explanation should mention this word. And here's an example. This is from the dataset ESNLI. The text is 3 people are riding a carriage pulled by 4 horses. Hypothesis, the horses are scrawny. The predicted class is neutral, meaning that the hypothesis could be true, could be false. We don't have enough information to say. And the explanation the model generates is the horses could be scrawny or not. Great. So now we do a counterfactual intervention. We insert this word joyous. This changes the model's prediction. Now it's predicting contradiction. So we know that this word was causally relevant to the model's prediction. And the explanation now it gives is the horses are joyous, so they are not scrawny. So it does mention this concept. So this is an example, this is some evidence that this explanation is faithful, right? It's mentioning the thing that is causally relevant. So we can run some experiments with this test. We can generate explanations by few-shot prompting pre-trained Llama 2 models, and we can run this on some NLP classification tasks. ESNLI, ComVE, ECQA. The important thing about these is that they are classification tasks, multiple choice tasks, and they have human explanations which we can use for few-shot prompting. And using this, we can compute the counterfactual test on faithfulness. So out of the examples where the intervention changes the predicted class, what percentage fail to mention the intervention in their explanation? Or equivalently, to compute faithfulness, what percentage do mention the explanation, the intervention in their explanation? And this is what this looks like. So this is faithfulness across the different data sets. The colors show the different model sizes. We tested 7B, 13B, and 70B. And there may be some trends. The larger models give slightly more faithful explanations, but the big difference is between the data sets. And this makes sense given our experimental setup. These explanations were all generated with very different annotator criteria, and if the model is just imitating these, it may imitate very different styles of explanation. So this can be informative about what kind of explanations are the most faithful, but there are some issues with the test. For one thing, it's trivially gameable. Given an explanation which repeats all of the input text verbatim, we'll never detect an unfaithful explanation, right? It'll just always mention the causally relevant word because it always mentions all of the words. So it's not enough to mention everything important. Explanations should also leave things out that aren't important. It also focuses only on discrete prediction changes, but the interventions may still be impactful even if they don't change the most likely class. So, an intervention that changed the probability of a class from 1% to 49%, even if it doesn't result in a label flip, it still has more influence than one that changes the probability from 49% to 51%, pushes it over that threshold. So I think that fixing these could lead to a more robust test for faithfulness. And here's a plot that kind of shows some of these effects qualitatively. So this is showing the relationship between the intervention impact on prediction and whether the explanation mentions the word. The x-axis here is the impactfulness of the prediction, which we measure by total variation distance, a measure of the distance between probability distributions before and after the intervention. So on the left, very non-impactful interventions that don't really impact the model's prediction. On the right, very impactful predictions. And then the facets here, the rows represent the data sets that we saw before, and the columns are the model sizes. So again, we see quite a bit of variation between the different rows, between the different data sets. Here, a steeper trend indicates a more faithful explanation, right? And what these things are plotting is whether the explanation mentions the word, whether it includes the intervened word. So what we want is for non-impactful interventions, the blue bar to be very small. We want it to not mention words that aren't impactful. And when the intervention is impactful, we want the blue bar to be very large. We want mentions to be very frequent. So we want this steep trend. In ESNLI, the data set on top, mention frequency does seem to be closely related to the intervention impact. But for ECQA, the trend is much flatter, even though according to the counterfactual test, faithfulness was quite high. So what's going on? We can look at some examples. So here's an ECQA question. What type of location would you find fish for sale? Refrigerator, ocean, pay debt, stream, market. The model predicts 5, market, makes sense. And the explanation it gives is quite long and verbose, right? Market is a place where goods are bought and sold. Fish for sale can be found at a market. Fish for sale cannot be found at a refrigerator, cannot be found at an ocean. It's quite templated, which results, I think, from the way that annotators were gathering the explanations on this data set. And you can see that when we have an intervention, like we insert the word elaborate, the explanation does mention this, but it's not really using it in any meaningful way, right? It's just kind of copy-pasting it into the explanation before fish. But it still says elaborate fish for sale can be found. Ocean is not a place where elaborate fish for sale can be found. Pay debts is not a place where elaborate fish for sale can be found. This explanation is long and includes a lot of stuff, but it's not particularly informative. It doesn't tell you whether this is an important feature. So we want a metric which captures the properties we've seen. And we introduced this metric, correlational explanatory faithfulness, which takes these kind of 3 inputs: an intervention, mapping an input example to a modified example; a measure of prediction impact, which takes this input example, intervention, and model, and maps it to a scalar representing how impactful the intervention was on the model's prediction, and a measure of explanation mention, mapping to a scalar representing the extent to which the explanation attributes importance to the intervened factors. So in our case, we just use kind of the binary metric of explanation mention, whether the explanation includes this word. And then we can compute the correlation between the prediction impact and explanation mention and use this as a measure of faithfulness. So using this word insertion as our intervention, we can instantiate CEF as a specific test, which we call the correlational counterfactual test. And this is what this looks like. So on the left, we have the plot again, faithfulness according to CT. On the right, we have correlational counterfactual test. And I think the interesting thing is this really does capture some of the trends that we were seeing previously, right? ESNLI is now shown to be quite a bit more faithful. The word mentions are a lot more informative of causal impact than ECQA, which has, high mention rate, but just high mention rate across the board. Seeing a word mentioned doesn't give you much information that that word was important. So in conclusion, I think the takeaways here, first of all, faithfulness is more than just causal dependency. We really need to look at the content of the explanations as well. It's highly dependent on how the explanations are prompted. And there is a slight trend in faithfulness for higher models, but a lot of the variation comes from the data set, here corresponding to different styles of example explanations. So this prompting, the way that you get the model to generate the explanations is really important here. And we see some trends for faithfulness, but none of them are perfect. I think consistent and reliable faithfulness will probably require some kind of training. I think it's important, therefore, to develop metrics that are robust to optimization, that we actually have some chance of training on. And I think another thing is that scalable oversight efforts might want to consider giving annotators these kinds of counterfactual intervention tools, right? If you want a human annotator to judge the quality of an explanation, maybe let them play with the model's input. Maybe let them change something. See if that explanation really is faithful, whether the model is really describing the true causal factors behind its decision. Cool, and please see our paper for more details. We just put it on archive. Thanks, I'm going to take questions.
Let's bring the lights up. One last round of questions.
Thanks for your talk. So I was wondering if the degree to which we're able to evaluate explanation also has an influence on our measure of faithfulness. So recent work by other people from Google, Ben Kim, showed that in order to evaluate explanation quality, for example, for the Go's 57th move, you need to have like a Go expert. Similarly, for chess, to like evaluate how well this move might influence the probability of you winning in the future, you need to have like a really good chess player. So how do you think us employing random annotators from mTurk or other platforms to evaluate the quality of our explanations, which then influences the quality of our faithfulness, influences the way we think about this problem as a whole? Thank you.
I think that's a great question. And I do want to clarify a distinction here between explaining why some label is correct and explaining why the model came up with this label. And I think maybe those are different questions, right? If we want to explain why the label is correct, that's more like plausibility. And yeah, there maybe you just get some external chess expert to come in and say, here's the possible game trees this could go. For faithfulness specifically, we really want the reasons that the model came up with this answer. So I think even if you have an expert annotator, it's not enough to ask them, why is this a good chess move? You need to run these kind of counterfactual interventions and actually verify your understanding. So maybe chess expertise would give an annotator like some knowledge of the hypothesis space of counterfactual interventions they could run. But I think you still need to test the model with these things. And I could imagine, the hope with this strategy is that we are going to be using it to oversee models which will eventually be more capable than us. So I guess I would still hope that even if you have a mTurker who's not a chess expert, maybe by moving pieces around, seeing how that affects the model's predictions, they could still get some sense of why the model is picking this move in this context.
Thank you.
More questions?
Thanks. Yeah, as well as the issue of how the chain of thought prompting worked for each of the different data sets, do you have a sense of whether it's there are some data sets where it's harder for a language model to generate a faithful explanation, maybe because the task is intrinsically more difficult or something like that? Are there other confounders going on there?
I think that's, a good question. I guess we haven't done a lot empirically with multimodal models, but I am curious the extent to which faithful explanations for visual tasks are feasible. I guess the criteria here is that you can have the best, most concise explanations if your reason for thinking something is concise, if it's dependent on a sparse set of features, or if it's dependent on the result of some search where you can just show kind of the branch that succeeded. If the model's actual criteria is something like linear regression on 200 features, and all of those features kind of appear to some extent, then I don't know to what extent we can compress this faithfully or usefully. So I think that's the property of the data set that I would be would think would most impact the feasibility of generating these explanations.
Makes sense. Thanks.
More questions?
Yep, thanks for the great talk. I was curious, is there some kind of connection to, for example, representation engineering? I feel, would it be possible to find a representation of faithfulness within models, or kind of have a representation of honesty as a proxy for faithfulness?
Yeah, definitely. I think that it would be very exciting to see if we could introspect into networks in the same way we can, there's been some work on finding honesty or deception features, find, is this explanation actually faithful? I think there is this interesting question of, do models actually know the reasons that they're giving an answer? Is it, when they are giving something unfaithful, is that because they're being deceptive or because they just don't know things? I think you see this in humans a lot, right? We often give an answer for something and we'll rationalize it. Maybe we don't even know the actual reason that we gave that answer. So I think that is a bit of an open question. And I think that's one reason measuring faithfulness separately from just honesty is important. We want explanations that explain what the model is doing, and we want we want to know what the model is doing, not just whether it knows kind of what it's doing. Does that answer the question?
Yeah, very interesting. Thank you.
Okay. That is, I am afraid, again, all we have time for. So thank you very much, Noah,
Cool.
for concluding our talks. Pleasure to have you.